Imagine you're standing beside a river in the Himalayas. It's a normal morning. The air is cold. The mountains are quiet. The river is moving through the valley like it has done for thousands of years. And then, without warning, the mountain begins to move. Not slowly, not as a small landslide. An enormous mass of rock, ice, mud, and snow suddenly tears away from the mountainside and races downhill. Seconds later, the river valley is no longer a river valley. It's a moving wall of destruction. Buildings disappear beneath brown, churning debris. Vehicles are pushed downstream. Bridges are ripped apart. And from a distance, the leading edge looks almost impossible to explain. It looks like a tsunami. Except there's one enormous problem. There is no ocean anywhere near this place. So how can something that looks like a tsunami appear thousands of meters above sea level? And why did it happen on what appeared to be an ordinary morning? The answer begins high above the valley. On August 26, 2026, a catastrophic event struck the mountainous region along the Nepal-Tibet border. Within hours, videos began spreading online showing the terrifying consequences. Sections of the Bordekochi and Trisuli river systems were overwhelmed. Roads disappeared. Bridges were destroyed. Hydropower infrastructure was damaged, and communities downstream were suddenly facing an enormous surge of debris and water. The scale of the disaster quickly became clear. Hundreds of people were reported dead, while many more remained missing as rescue crews struggled to reach isolated areas. At first, investigators had several possible explanations. Maybe a glacial lake had suddenly burst. Maybe an earthquake had destabilized the mountain. Maybe extreme rainfall had produced a massive flash flood. But then, something strange appeared in the seismic data. Instruments had detected a powerful ground signal shortly before the flood arrived. It initially looked like an earthquake, but there was a problem. The ground had shaken because the mountain had collapsed. The source wasn't a tectonic fault. It was something much bigger moving violently downhill. Satellite imagery helped reveal what had happened. High in the mountains, around 5,200 meters above sea level, a huge section of ice and rock had broken away. Imagine a mass weighing millions of tons, sitting on an extremely steep slope. Now imagine that entire mass suddenly losing its support. It plunged roughly 1,200 meters down the mountainside. That's an astonishing vertical drop. And as the material accelerated, it didn't behave like a single solid block. The ice shattered, the rocks collided, the mountainside fragmented, and everything began spreading outward. Scientists call an event like this a rock-ice avalanche, and these avalanches are among the most powerful mass movements on Earth. The impact can be so violent that seismic instruments hundreds of kilometers away may interpret the vibrations as an earthquake. In other words, the mountain created its own earthquake signal. But that still doesn't explain the enormous wall of muddy water seen in the footage. For that, we have to look at what happened when the avalanche reached the valley floor. Because the avalanche didn't simply cross the river, it consumed it. As the enormous mass rushed downhill, it collided with water, saturated soil, loose sediment, boulders, and debris already sitting inside the valley. Instead of stopping, the moving material began collecting everything in its path: rock, mud, water, ice, trees, sediment. Everything became part of the same moving mass. This process is known as entrainment, and it can transform a dangerous landslide into something far more destructive: a debris flow. Think of wet concrete moving downhill at extraordinary speed, except this concrete contains boulders weighing several tons. The terrifying part is that the avalanche can actually become larger as it travels. The river doesn't necessarily weaken the avalanche. The river can become fuel for it. Water mixes with sediment and broken rock, reducing friction and allowing the mass to continue flowing downstream. So the footage isn't showing a normal river suddenly overflowing its banks. You're watching a mountain collapse and progressively turn itself into a flood. That's also why calling it a tsunami is misleading. A tsunami is fundamentally a wave. Something suddenly displaces a large body of water, and that disturbance travels outward through the water. Here, there wasn't the wave traveling through an otherwise stationary body of water. The water, rocks, mud, ice, and sediment were all moving together. The entire mass was advancing downstream. And the almost vertical front, that's a characteristic of extremely large debris flows. The heaviest rocks and boulders can concentrate toward the front, creating an incredibly dense and destructive leading edge. Behind it, wetter mud and water continue pushing forward. It's almost like a gigantic bulldozer, with an entire river pushing from behind. But there may have been another complication. Researchers are also examining whether the avalanche temporarily blocked the river. Picture millions of tons of rock and ice suddenly filling a narrow Himalayan valley. For a short period, it could act like a natural dam. Water begins accumulating behind it. The pressure rises, and eventually, that temporary barrier can fail. When it does, the stored water may be released in a sudden pulse. That possibility could help explain the extraordinary rise recorded downstream. One monitoring station reportedly observed the river level increase by several meters in a very short period. The exact sequence is still being investigated, but the timing is disturbing. The initial mountain failure appears to have happened in the morning. Soon afterward, the river system began rising catastrophically. For communities downstream, that could mean there were only minutes to react. And this reveals one of the biggest weaknesses in traditional flood warning systems. Most flood monitoring is designed around predictable signals: rainfall, river levels, weather systems, storm systems. But what happens when the disaster begins with a mountain suddenly collapsing in a clear morning? There may be no heavy rain to detect, no slowly rising river, no obvious storm approaching. By the time a downstream gauge realizes something is wrong, the destructive flow may already be moving towards it. And in the worst cases, the monitoring equipment itself can be destroyed by the flood. That creates a frightening problem for the Himalayas. The danger isn't necessarily coming from the sky anymore. Sometimes, the danger is coming from the mountain itself. So, why did this particular section of the mountain fail? That question may be even more important. Satellite observations indicate that the source region had experienced significant snow loss during a warm period before the event. Rapid melting can allow water to penetrate cracks in ice and rock. That water can weaken the connections holding unstable material together. And across the Hindu Kush and Himalayan region, another long-term change is taking place. Glaciers are losing mass. High-altitude permafrost is warming. Rock that remained frozen and stable for centuries can become increasingly fractured and unstable as temperatures rise. That doesn't mean every glacier is about to collapse, but it does mean some high mountain slopes are becoming more vulnerable to sudden failure. And this disaster didn't happen in isolation. The Himalayan region has experienced other devastating floods, landslides, and glacial outburst events in recent years. Scientists and mountain researchers have repeatedly warned that a warming climate can increase risks from unstable glaciers, thawing permafrost, landslides, and rapidly changing water systems. The event of August 26 is therefore more than one terrifying collection of viral videos. It is a warning about how complicated mountain disasters can become. A glacier and mountainside can break apart. The resulting avalanche can fall more than a kilometer. Its impact can shake the ground so strongly to resemble an earthquake. Then, the avalanche can enter a river. The river can become incorporated into the moving debris. The debris flow can grow larger as it travels. And eventually, what began as a collapse high in the mountains can become a wall of destruction moving through communities many kilometers away. That's what makes these disasters so terrifying. The flood isn't necessarily born in the river. It can begin kilometers above it, inside the mountain itself. And behind all the satellite images, scientific explanations, and terrifying footage is the part that matters most. People lived in those valleys. They woke up expecting an ordinary morning. They had no reason to believe that a mountainside hundreds or thousands of meters above them was about to collapse. There was no ocean, no giant storm, no obvious warning, just a mountain that suddenly stopped being still. And when millions of tons of ice, rock, mud, and water begin moving downhill, there's very little that anyone standing below can do. For the scientists studying this event, the challenge now isn't simply understanding what happened. It's figuring out how to recognize the next unstable mountain before it moves. Because in the Himalayas, the most dangerous flood may not begin with rain at all. It may begin with the mountain coming down.